Hi, I am Alas Rasim, a civil engineer with over 40 years experience in the field. I've worked on everything from on-site execution to detailed structural design work on the computer. These days, I focus on automating structural calculations and sharing my knowledge with others who are passionate about structural engineering and analysis. If you are into practical tips, engineering insights, and automation in structural design, you are in the right place. In this video, I will show you how to automate structural calculations using Excel spreadsheets by creating your own calculator for design reinforced concrete slab. You will learn how to use spreadsheets like Excel to perform basic structural design and calculation tasks. Whether you are a student, engineer, or just curious, this is a practical guide you can apply right away. Section 1. What you will learn. We will walk you through setting up a calculation sheet, inputting loads and section data, automating formulas for bending moment and shear force, and checking design limits using Eurocode formulas. Section 2. Why use spreadsheet for design? Spreadsheets offer speed, flexibility, and repeatability. Instead of doing every step by hand, you can build smart templates that adapt to new inputs. That means fewer errors and faster results, especially for common elements like beams, columns, and slabs. Section 3. Example. Slab design step by step. Let's design a one-way reinforced concrete slab with a height h supported on two walls with thickness t. The effective span of slab must be equal to a clear span Ln plus A1 plus A2, according to Eurocode 1992-11 Article 5, 3221. Step 1. Define inputs. In column A, we list inputs. Material properties of concrete and steel, dead loads and live loads, slab dimensions and wall dimensions, clear span and effective length of the span. Here is the list of the input data: concrete strength, yield strength, dead loads, live loads, design loads per meter, slab thickness, distance D, support thickness, distance A1, distance A2, clear span, and effective length of the span. In column B, we fill in the values of the data listed in column A. The input values in column B are entered in the gray cells. Other values such as design loads, distance D, distances A1, A2, and the effective length of the span are calculated based on the input values and placed in orange cells. This means that you only need to fill in the cells in gray. Step 2. Calculate reactions and bending moment. We assume that the floor is divided into beams with a width of 1 meter. We use simple formula for the maximum bending moment, M equals QL square over 8. Excel handles these with basic cell formulas like B7 times B14 square divided by 8 and divided by million to convert Newton millimeter to kilonewton meter. Step 3. Calculate reinforcement. Excel handles these with basic cell formulas like B16 divided by B3 times 0.9 times B9, multiplied by million to convert the moment unit kilonewton meter to Newton millimeter. Step 4. Calculate the percentage of reinforcement. Excel handles these with the basic cell formulas like B18 divided by 1000 times B9. The 1000 here is the width of the previously assumed beams with the width of 1 meter. This percentage must be checked with the minimum and maximum reinforcement. And these percentages depend mainly on the strength of the concrete and the yield strength of the steel and the tension zone. Reinforcement percentage of this floor is 0.86. This is between the minimum percentage of 0.13 and the maximum of 1.03. Step 5. Conditional formatting. In Excel, conditional formatting is a feature that automatically changes the appearance of a cell, such as the background color, text color, or border based on the value in the cell or a formula you set. This example shows how the colors and annotations are adjusted in response to exceeding the maximum reinforcement threshold by increasing the live loads, and how the condition is met again after increasing the slab thickness. Step 5. Choose reinforcement per meter width of the floor. Here, phi 16 per 120 mm is chosen as main reinforcement in the tensile zone, and phi 8 per 120 mm as transverse reinforcement. For coincidental end moment reinforcement is 0.15 times 1.25 of the main reinforcement, using phi 8 per 120 mm, and for transverse reinforcement using phi 8 per 250 mm. Here is the general reinforcement drawing of the floor, and next to it, the details of the end moment reinforcement. This is more than just videos. It's about building something that lasts. Join us. Like, share, and subscribe. Together we're stronger.